Okay, so one more thing I wanted to tell you about was this thing called atom optimization. Um, Optimization. And this is essentially a better, faster way to do gradient descent. And it uses two tools, which are called momentum and RMS prop. So, in order to teach you about atom optimization, I first have to tell you about these two things. But before that, I want to give you a slightly more sophisticated sense of what's going on in gradient descent. Okay, so again, we have this parameter W. We might have a lot of parameters W, but let's say we consider them one at a time, right? And as that one parameter of W changes, what is the effect on the cost function J? And I told you to visualize it in the sense of uh, something like this, a parabola. And so it turns out that it's exactly like a parabola in terms of linear and logistic regression. But it's not exactly a parabola when it turns to neural networks and more complicated functions. But you can still visualize it something like this. So even in a neural network, it'll be something like this, let's say, right? And um, the optimal function, optimal value for W, which is the weight, would be somewhere around here because this corresponds to the lowest possible cost across the whole cost function. So that would be the optimal value of W. But you can see over here that there is this what we call a local minimum here. So this is kind of smaller in value and cost compared to anything that's sort of locally around it, right? And that means that if we are over here, then we will be kind of wanting to go in this direction. And if we're over here, then will want to go in this direction. And we'll essentially settle down over here. So a lot of times when you're training neural networks, what tends to happen is you have these things called local minimums that if you settle in those local minimums, then your cost can't break that boundary and go to what we call the global minimum. The global minimum is essentially the minimum across every part of the cost function, not just locally. And so one of the visuals that I wanted to give you, instead of this part right here, I'm going to delete this. So one of the visuals I wanted to give you was a ball rolling down a ramp. So we'll start with the parabola visualization from before. Second. Um, so something like this. And if, let's say we're over here, this is our initial value of W, and like W0 maybe, and that corresponds to a cost of this. So this is our point right here. We can actually visualize this as a ball just sitting there at that part of the half pipe, I guess. And in terms of like you know, what gradient descent is doing is it's applying gravity to this ball and it's sort of pulling this ball to go down. And your value of alpha, which is your learning rate, is determining how fast that gravity is acting, or like what is your gravitational coefficient, I guess. And so if alpha is really like large, then it's almost like you're pushing this ball. You're not just dropping, you're actually pushing it down this ramp. And so what happens is that if the value of alpha is too big, you can visualize this as you just push it with a lot of force down this ramp, and it ends up maybe rolling all the way up here because you pushed it with so much force. And a small value of alpha would mean that there's a very high amount of friction that's on this ramp, right? And so this ball is, sort of going down, but it's going down very, very slowly, or the gravitational coefficient is very small or something like that. So it is going down, and eventually it will go down, but I want to get in your mind that this can be interpreted like a ball, and just a ball that's sort of um, going to maybe roll from here to here, and then there's the ball, and then here to here, there's the ball, and then again and again, and maybe it oscillates a little bit, and then it settles down in the minimum. So that's how I want you to think about gradient descent. So going back to the previous example where you have something like this, where there's a local minimum, but there's also a global minimum. So let's say we start over here. If we start over here, then think about it, like in terms of a ball, that the ball would sort of be dragged down this way and maybe oscillate to here, then oscillate to here, then here, then here, and here, and then it would settle down right there. And that would be our value of W that we end up with. But instead, if we started here, then almost surely, unless our value of alpha is too big, we would settle down over here, right? But now let's say it was over here and the value of alpha is really big. So it would be like us pushing it down here. It might actually go past this hill and end up over there. And it might get into the global minimum anyway. So it might skip the local minimum. So this is definitely like all possible. It all depends on your value of alpha. It all depends on your cost function, which actually depends on your architecture of your neural network. Like I said, in linear regression, logistic regression, it's actually a parabola, which means that you can analytically solve for the solution, meaning that you don't actually have to do gradient descent technically. You can just analytically, algebraically solve for what is the optimal value of W if for each of your parameters W. Um, but in case you're doing gradient descent, it's most likely will never go wrong unless your value of alpha is just too big and you end up going all the way up here or something like that. Um, so that visualization being said, I want to go down over here. And so you can see this is another visualization of where you have theta is just another symbol for W. So theta is being used here instead of W. So it's like theta 0 and theta 1. And the cost function is on the z-axis, where the height of this is essentially telling us the cost or how bad the model is doing it at those values for theta 0 and theta 1. So this is sort of the same thing in 2D where you can think of it like if we're starting over here and you put a ball over here, then you think of this like a landscape where you sort of have these hills and then you have these divots. And what you're trying to do is place the ball here and just let it be influenced by gravity. And that's what gradient descent is doing. So gravity is probably going to pull it down this hill and then eventually it's going to roll over here and it's going to roll over here, and then it's going to be sucked into this lower part um, by gravity, and then it's going to sort of just stay there. After it reaches this point, it's probably not going to go anywhere else. So if you have a good value of alpha, this is what should happen, I guess. Um, but now you should start to see have a better like understanding of gradient descent, what's happening behind the scenes. And with that being said, I want to transition into the first part of atom optimization, which is momentum. Okay, so one of the key things to understanding momentum, and I guess also RMS prop, is this idea of exponentially weighted moving average or averages. Um, and so here you can see that over a lot of days, there's a temperature reading for all of them, all of the days. And it's very noisy. That's what I want to point out to you. It's very noisy that it's sometimes up and sometimes down and whatever. And basically, we want to find a way to, have it not be so noisy. And that's what exponentially weighted moving averages does. So here you can I'll basically tell you how we do it. So let's say um at each time step t like so at each time step like t I get in a reading x um ti, let's say ti is the time step, then the reading is xi. So for time step 0, my reading is x0, and then time step 1, the reading is x1, time step 2, the reading is x2, and so on and so forth. So the way that the exponentially weighted moving averages works is that the goal is to have a smooth transition. So let's say you start like we want to create a new graph that looks like this, right? And over here we still have a value for t0, t1, t2 all the way, right? But it's much smoother and less like up and down than the original data, right? So we want to create something that's much smoother. So let's say that we're creating a new series, right? Times 0 corresponds to y0. Time 1 corresponds to y1. And I'll tell you what all of these are in a second. Y2 and so on and so forth. And let's say, for sake of argument, that we just let y0 is equal to x0, right? And y0 is our new function that we're trying to, so this is the new smooth data. That's the goal of this. It's the like transformed new smooth data, right? And it's less like variable in terms of how it changes every time step. So let's say initially it's just whatever the initial value was for the original time series. Then what we can do is if we set y1 equal to x1, then that's just copying what we had initially, right? But instead, if we make a change, let's say we make a change that we have we take an average, right? So we're going to take half of this and then plus y0 times 0.5. We take the last reading over here and then we multiply that by 0.5. So so essentially we're taking half of the new signal and half of whatever we've been collecting over the old signals. Okay? And so let's say we do y2 is equal to the new value of x. So x2, right? Times 0.5. So we take in half of the new signal plus y1 times 0.5. So you might be thinking, why am I doing 0.5 and 0.5? It's because 0.5 plus 0.5 is equal to 1. So in total, like my coefficient is 1. It could be 0.7 and 0.3. So I could have had made this 0.7 and this 0.3. But these essentially have to add up to 1 in order for it to actually be an average of two values, right? So I'll take that out. And for now, I'll just keep it simple. I'll take half of the new signal and half of the signals that we've been collecting over time. And then y3 would be equal to whatever the new value of x is that we're getting in, which is x3. And we're taking half of that signal. And then plus y2 times 0.5. So half of the old signal. And so you can see over here what's starting actually maybe not. Let's expand this out. So this right here would just we can replace this with x0. So if in case we want to change everything on the right side to x's instead of y's, this could be turned into x0. This right here could be turned into x2 times 0.5. That's okay. But we want to get rid of the y1. What is y1? x1 times 0.5. x1 times 0.5 plus, actually I have to put this in parentheses, plus x0 times 0.5, close parentheses, and then we have this 0.5 at the end, right? So all of this is just y1. This is all just y1. And then this is multiplied by 0.5. And then we have x2 times 0.5 plus, let's say x1 times what? Times 0.5 squared. 0.5 squared. Actually, this is not 0.5 squared. This is 0.5 to the power of 3. So, no, this, wait, sorry. This is squared, sorry. Yeah, this is squared. And then plus x0 times 0.5 and then squared. Okay. And then we have over here, we have for y3, the first term is okay. X3 times 0.5 plus 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 whatever y2 is, right? So this is x2 times 0.5 plus x1 times 0.5 squared plus x0 times 0.5 squared. And then I think all of this times this 0.5. So this is equal to x3 times 0.5 plus x2 times, there's 0.5 there and there's a 0.5 there. So it's a 0.5 squared plus x1 times 0.5 to the power of 3 plus x0 times 0.5 to the power of 3. Okay, so now I think we can start to understand what is y3. Okay, I think this is really crucial to look at. So initially y0 is just x0. We're not actually doing anything to the initial value of x. But now we have this y3 is a very, very complicated term, right? And what is this exactly? So all we did, the rule was very simple, right? The rule was very simple. We just took the new value, whatever corresponds to the third time step of the original series, right? This is the temperature on the third day or whatever. And then times 0.5 plus whatever we've been collecting, the previous time step in our exponentially weighted moving average, times 0.5, right? And notice that these two things add up to 1. That's a rule that should be obeyed because of the law of averages, I guess. And then over here, this is y3 is equal to x3 times 0.5 plus x2 times 0.5 squared, x1 times 0.5 cubed, x0 times 0.5 cubed. So what we can do here is start to understand what is the weightage of, so let's actually add up all of these things. 0.5, 0.5 plus 0.5 squared plus 0.5 cubed plus 0.5 cubed, right? And if we do this on a calculator, or actually this is just 0.5 plus 0.25 plus 0.125 plus 0.125. And then this is all equal to 1. I think you can calculate this for yourself, but the sum of all of these things is equal to 1, right? So the sum of all of the coefficients of x3, x2, x1, x0 is equal to 1. And what does that mean? That means that we're actually taking some sort of average between, so y3 is some sort of average of x3, x2, x1, and x0. It's an average. But what is it's a weighted average, right? So we're not giving the same weightage to each of x3, x2, x1, and x0. Since x3 is being given a weight of 0.5 and x2 is being given a weight of 0.25 or 0.5 squared, right? And so in seeing this, like, we can start to understand that x3 is given the highest weight, x2 is given the second highest weight, x1 and x0 are given very, very small weights. And as we start to do this for so instead of y3, if you did this for y4, y5, y6, y7, and so on and so forth, what you would start to see is that the weight corresponding to, so this would always be an exponentially weighted moving average. This would always be a weighted average of all of the previous x values. So let's say we were doing it for y7. Then it would be doing a weighted average between x7, x6, x5, x4, x3, x2, x1, and x0, right? But the weightage given to x0 by the time we reach to y7 would be so small that it literally wouldn't be taken into account, right? And then x1 as well would be very, very small. And then x2 would be still very small, but not as small as x0 and x1. And then x3 would be very, very small as well. And then x4 a little bit larger. And then the most weightage like 50% of the weightage would be given to the x 7, which is the one that corresponds to the time step, that particular time step. So um yeah, so what we can see is, for even for like y2, let's say, right? Y2 gave a weightage of 0.5 to x2, and then over here we have 0.5 squared. So it's been discounted by a factor of 0.5. And so this one was 0.5 squared over here for x1, and x1 has 0.5 cubed over here. So each time the factor is being multiplied by, 0.5, and then 0.5 and 0.5, and then you have this exponential decay. So eventually whatever x0 is, x1 is, x2 is, those won't matter, and then everything that's at that time step, let's say x10 or x15, whatever. If you're calculating y15, then x15 would be the most important. Um, but yeah, I guess that's the way of doing this, like doing this exponentially weighted moving average. And remember how I said that this could be 0.7, this could be 0.3? So I want to go back to this graph over here and say, basically, let's say we said y at any particular time step was equal to 0.999 times x xi. So the reading of x at that time step plus 0.001 times yi minus 1. Yi minus 1 is just the y from the previous time step because this is yi. So we're taking 0.999 times x1 and then plus 0.001 times I minus 1. And then, so what does this mean? This means essentially this is almost just 1, and then this is almost just 0. So this is almost just xi, right? So you're essentially just setting yi to be equal to xi almost. If this thing is very close to 1 and this thing is very close to 0. Conversely, if we have yi is equal to 0.000, oh sorry, 0.001 xi plus 0.999 yi minus 1, then essentially this is almost 0 and this is almost 1, right? And this yi would just be almost equal to yi minus 1. And so we would have almost constant. It would just be like yi, in order to get yi, you would just look at yi minus 1 and you would just copy that over and then copy that over for the next time step and the next time step. And so it would be so smooth that you would just not be doing anything, right? And so if this first number, which corresponds to the current reading, is higher, then you're taking the current reading more into account. And so since the assumption is that your original data has a lot of variability, those blue points, which are the original data, have a lot of variability. That's the assumption. If your value, your first value over here that corresponds to this 0.001 in this example is very close to 1, then what will happen is that your data will have your series of y will have more variability, right? And it will be less smooth. If it's closer to 0, then it'll be more smooth and have less variability. But it might not have there are advantages and disadvantages to both. Because if it's very close to 1 and you have a lot of variability, then what would happen is that you capture more of the data, but you're not really smoothing anything, right? And that's what this first example is. So there's no smoothing really going on over here because you're essentially just setting yi equal to xi. And in the second example, there's too much smoothing going on because essentially it's going to be like it's just going to be like a flat line, right? And so you want something in the middle so that it's smooth, but it also, takes into account what the data is. And so here, the red might correspond, the red line over here might correspond to this value being more close to 1, but not that close, I guess, but more close to 1. So let's say 0.7 maybe. And then this But let's see, what is the smoothest one? The smoothest one looks like the purple one. Let's say the green one is less smooth than the purple one. So this might be, so I said 0.7 corresponded to this value, right? That corresponds to xi. So this might correspond to 0.5, right? And then this might correspond to like 0.3 or something like that, which is the furthest away from 1, right? So this is probably the closest to 1, 0.7, right? I said for red, and then maybe 0.5 for green, which is less smooth, and then uh, second smoothest, and then the purple one, which is the most smooth, would probably be something like 0.3, very far away from 1. So now that you understand exponentially weighted moving averages, I think it's time to go on to momentum.